Here's where we stop. Okay, let's get started. The kind of getting ready to wrap up some of this. With multiple regression, because we typically don't have, because the independent variables typically are correlated with each other, we generally don't have uncorrelated predictors. We often refer to our regression coefficients B as partial regression coefficients. And that's just a way of kind of acknowledging or keeping track of the fact that they're based on other variables being controlled for, other variables being in the model. So they're not going to be equal to the simple correlation. The standardized betas are not going to be the same as the simple correlation. So if you hear people talk about partial regression coefficients, that's again, it's just a way of referencing the fact that it's multiple regression with correlated independent variables. The kind of looking at the regression equation, kind of another way of thinking about this, or I guess just kind of summarizing, when you're looking at each of those regression coefficients, remember, that's the effect of that variable if the other variable doesn't change. So B1 is the effect of x if x2 doesn't, B1 is the effect of x1 if x2 doesn't change. The regression coefficient for study hours is the effect of study hours if school quality doesn't change. That's another way of thinking about holding constant. It's if school quality, if you can make kids study more with no impact on school quality, not with school quality not changing, I should say, that's the effect you would expect to see. But the problem is often when they're correlated because they do change with each other. That's what correlation tells you. So you do see kids in higher quality schools maybe study more than kids in lower quality schools. So in the real world, they do go together a little bit. And what we're talking about then with multiple regression is its statistical control. Right? We're not being able to experimentally control like with the mice that we can say, we can make the mice do things for us. We're not able to say, you know what, this school's a horrible school, but your kids are going to study 10 hours a week no matter what. And that's a really great school. Now you've got to make your kids not study. Because we can't do that, that sort of experimental control, we do statistical control instead. And that's what this is all getting at. We're pretending, basically, as if we could change x1 without anything happening with x2. That we could look at the effect of maternal education and smoking as if we could make women smoke or not smoke, which of course you can't. I mean, as a result, as much as I love I love stats, and I love elaborate modeling, this is still kind of straightforward stuff. I love it when it gets messy and elaborate. It's still not as good as experimental control. If your point is to draw conclusions, if you want to understand, does this have an effect? Statistical control is just not as good as experimental control. It's not. Ultimately, we are pretending as if we could make the variables uncorrelated with each other, but when we can't. Now, again, there's ways that you can help that. That's another reason why we like random assignment in studies. Because if you can randomly assign people into an intervention, you don't have to worry about all the kids who have really on-the-ball parents that are at the schools and know what's going on and they're invested in their kids' education. And there's this new science program coming in, and gosh darn it, they're going to make sure their kid gets that science program. But they're also the higher income, more educated parents, more engaged parents. If you're able to randomly assign the kids, you'll get just as many engaged parents in the intervention as unengaged parents in the intervention, and it'll all balance out. And your predictors, all those confounds, all those things that go together start to disappear. So that's another reason why we like experimental design. That it helps to make sure, particularly for interventions, it helps to make sure that the intervention status is uncorrelated with all those other variables. They may be correlated with each other, but they're uncorrelated with the intervention status. So again, that's kind of my soapbox. As much as I love statistics, we're doing all these fancy-dancy, elaborate methods because we can't do experimental studies, because we can't do experimental control. We're left doing statistical control. Okay, so that's Venn diagrams. I kind of digressed there a little bit. It's a nice visual way of looking at things. There's other visual ways that we're actually going to see more in the semester, and particularly in a couple weeks. And you'll see a lot if you go on to take a structural equation modeling class after this one. That's like the second half of this book. The one is path modeling, and we're not going to spend too much time talking about it now, other than just to kind of put it out there as a way of visualizing what regression is doing. And with a path model, the idea is you have your predictor variables, and we have these arrows just saying these predictor variables are related to that outcome. So the arrow just tells you which way the effects go. These predict grades. The two-headed arrow here says, and school quality and study hours are correlated with each other. Notice there's a one-headed arrow. I'm not saying grades predict studying or grades predict school quality. It's these cause that. These cause, I arguably shouldn't even be saying prediction, but well, that's interesting. Well, anyway, the one-headed arrow says this has a causal effect on that. The two-headed is a way of saying they're correlated with each other. I have no idea which one's causing the other one. Maybe they're both causing each other. I just don't know. So I'm kind of stuck saying they're correlated with each other. How big these effects are generally described based on beta, the standardized regression coefficients, though they don't have to be. In fact, I was actually kind of pleased. The book brings up sometimes, I just had an issue with a reviewer a while ago because we didn't report standardized betas because we were one of these situations that they talk about that you can't, it doesn't always work. So I have to explain that to a reviewer. So anyway, so that describes these effects. Notice these are boxes because they're measured variables. They're things, they're a real variable I have real data on. And then over here there's this thing R1, that's our residuals. That's that kind of leftover stuff we don't know about. And that's in a circle. And that's also influencing grades. This R1 is everything else that's influencing grades that we don't know about, we don't have measured, it's not in our study, other than these two. Okay? We're actually going to be doing this towards the end of the semester. Even a little bit more elaborate models where you're going to be calculating all these different paths of how A influences B and B influences C and direct effects. And well, we'll get to that in just a sec, what those mean. So that's another way. So that's kind of ways of conceptualizing what multiple regression is doing. Now let's take a step back a second and delve again a little deeper into what's going on in a regression analysis. What are some of the aspects of it that we can use? So looking back, let's take a step back, looking at the residuals for a minute. And here's our regression equation, right? We're back to where we were at the start of the class, looking at school quality, study hours, predicting grades. Here's our regression equation. Our residuals, right, that's the observed score. Someone's observed grades minus whatever their predicted grades were based on that equation. Now we can actually go through and calculate the residuals. Now SPSS, all the software will do it for you. You don't have to, you just need to tell it to give me residuals, and it'll do that. But let's say here we've done that. So here's just a subset of the data. Grades, each row is one child. Here's their observed grades. PRE1, that's based on the model. That's their predicted grades. And RES_1, that's their residual. So you can see this kid's really struggling. His GPA is 0.037. Ooh, ouch. Is predicted, he should be is predicted to be a 1.75, so the residual is negative 1.38. He should be up here, he's down here, so the difference between observed and predicted is a negative 1.38. And just to kind of check, right, remember the predicted plus the residual should be the observed. So here I've just calculated grades minus the predicted plus the residual. And the fact that it's 0 tells you, yep, it worked exactly the way we thought it should. Yeah, it's kind of unnecessary. But to make the point that your predicted plus residuals is the kid's grades. So you can go through all of these and see kind of, sometimes the residuals are big. That's a big negative. Sometimes, oh, there's another pretty big negative. Here's some positives. I should have, on average, it'll all balance out for the residuals. It seems it didn't in this subset that I selected. But you can go through, again, everyone has their observed score, their predicted score, and a residual, what's left over. Now, we can take these predicted scores, so let's kind of think about it. Those predicted scores, they're my estimate of what the outcome is based on a set of independent variables. So I'm trying to guess what an outcome score is. I'm looking at the outcome. I've got these predictors. I'm using those predictors. I calculate a regression equation. I get betas. I come up with the best possible estimate of the outcome I can get to come up with my predictor, my predicted score. So the predicted score is kind of related to my outcome based on my set of predictors, and probably as well related as possible. Well, based on that, it's kind of cool if you do a correlation between the predicted scores and the outcome. The correlation between the predicted scores and the outcome is 0.27, which, no coincidence, is exactly what the R is, the multiple R. Now, remember, R squared is the variance in the outcome related to the set of predictors. Well, that's kind of, you can think of the predicted score is information based on my set of predictors. It's where I've linearly combined. I've done that regression equation. I've combined all those predictors, all those independent variables, specifically to predict the outcome. So the predictors are the predicted scores are gonna be we expect them to be correlated with the outcome because, right, that's the whole purpose of doing the regression. We're trying to come up with predictions that are as close as possible to the outcome. So we expect them to be correlated with the outcome. And that's how correlated with the outcome is going to be directly related to R and R squared. Counts for that much of the variance in the outcomes because it's the same thing in a way. It's conceptually both, whether we're looking at the R squared, remember an R is just the square root of R squared. So the predictors are again, we've combined our predicted score. Our predicted scores is a combination of all those independent variables that's related to the outcome. How related to the outcome? Well, we know that that set of predictors was related to 7.3% of the variance. So how related is that set of predictors? 7.3% of the variance worth. How related is the predicted score? 7.3% of the variance, because it came from the same place. Maybe that's the way to describe this. You can see I'm kind of stumbling with how to conceptually describe this. It's coming from the same place. It's coming from the same set of information. So they're related. Now, kind of why this is useful, that once you can start to see that, well, these predicted scores, right, there, so I've got my independent variables, and I'm just kind of switching gears. I know I like to say predictor variables because they're really not independent variables, if you're a purist, because we're not, because it's not experimentally assigned. But to kind of keep the language a little clear, we're going to call them, I've got my independent variables. I use those independent variables to calculate regression coefficients. I then multiply those regression coefficients by the independent variables to get my predicted scores. The predicted scores are going to be pretty correlated with the outcome. The better the model, the more correlated my predicted scores will be with the outcome. And in fact, if it's very correlated, one thing that you're seeing, there's newer statistical techniques that people will come in and say, well, you know what? They're sufficiently correlated. What happens if you're missing grades in my case? So you got a bunch of kids. Some kids are missing some variables. You can do a multiple regression using the other variables to predict what that score would be. And you use it as a substitute. You use it as a composite for that variable. So there's a whole, I should have popped this slide up a minute ago. So you can think of that, you can think of the predicted score as a new variable that's going to be hopefully, it'll be correlated with whatever your outcome is. And we know exactly how much correlated it'll be. It'll be whatever the R was for your model. That's how correlated the new variable, this composite. And it's a composite because it's a new predictor based on all those other variables, all the independent variables, that's going to be correlated with your outcome. The R tells you how related that predicted score is to the outcome. The R squared gives you the proportion of the variance that's in the outcome that's related to this new composite predicted score. And again, if they're high enough, if it accounts for enough of the variance, you can potentially use it to replace as a substitute for the outcome. So there's a whole group of missing data analysis. There's like a type of approach when you have missing data, which you often have in real world research. Some kids are, you're collecting data on college students, and you don't know what everyone's high school GPA was, for whatever reason, or they didn't get, there's some information that's missing on applications, or I want to look at the relationship between these school variables and kids' grades, and sometimes I'm missing things. You're always missing some data. You can use this as an approach, or people have been developing techniques to use this as an approach to estimate what that missing data would be. And then plug these new composites in. It's not the same thing. It's not grades. But it's like, well, this is what, based on this relationship, based on all this data, that's what I predict their grades would be. And you can plug that in as a replacement, as a substitute for the missing data, and then run your analysis without dropping that subject. Now, if you're really clever, there's approaches that go in and they take into consideration just how good that relationship is. How much, because notice we look at those scores. There's some of these that are really close, and there's some that are really far off. So one approach is you say, okay, I'm going to do this, instead of just doing this once, instead of just predicting the score and plugging in that predicted score and just doing one regression, you do 10 or 20 or 30 regressions. And every time you find that missing data, you recalculate it. Now, of course, you're going to recalculate. You're going to get the exact same predicted score, but you throw in random error based on how much random error there is in the residuals. So that you added a little bit of noise, saying, well, I'm not, there's a lot of noise here, so you build in noise. This is getting way beyond. I didn't mean to go this far on this, but it's kind of cool to get a sense of what's going on out there, and very innovative ways that I was initially extremely skeptical of, and I've slowly warmed up to. Because I still want to say, you're making up data. It's like, it's not, you're making up data. But when you think about it, and there's been some studies that have experimentally kind of looked at this, it can be an effective way to deal with missing data with all sorts of assumptions. So anyway, this notion, the idea that your predicted score can become a variable all on its own, and that it's a summary of all of those other variables aimed at trying to describe whatever the outcome is useful. And in fact, you'll see, I think the book has like a little aside talking about, you kind of see that idea used in other ways beyond how I've just described it. That you come up with regression models to create other sorts of composite variables that are then used for estimating things like parental warmth or more abstract sort of concepts where you can't just ask how many hours did you study. It's hard to say, I can't monitor you and find out how much you loved your mother. That's a tougher thing, or how much your mother loved you. So anyway, we'll kind of digress. This is kind of interesting. It's tossing out there for you to think about. Another thing the book talks about